So as usual, for the Life After Code in Place, this is for people 18 years or older. If somehow someone under 18 is here, we would ask that you leave now and watch the recording, which will be available before too long. And no attendance records or grades or recommendations. We're here for the joy of learning. And this will be recorded, so if you don't want your face or your name there, just make make your name, take off your last name or turn off your camera. And ask for professional behavior as always. So last week we talked about NumPy and pandas, and we will use those pretty heavily today. Today we'll just get a brief introduction to data science using using those techniques. And the nice thing about data science is without being a hardcore Python expert, you can actually accomplish a lot these days online in data science, and we'll see some examples of that. And then we might talk about this much about machine learning toward the end. So there's a lot of good things going on this week. There are some videos available. Martha will have office hours 23 hours from now, tomorrow. There'll be some, and next week, 1 hour earlier than now, still Tuesday, but 1 hour earlier, Vicky, the Pie Whisperer, will give a presentation on images. So that'll be something good to look forward to. And there's some instructions on how to prepare for that as well. And then 2 weeks from today, we'll be back to the same time talking about nested lists. So a couple weeks ago, we briefly introduced collabs and we used them last week. So let's just briefly review them. If you log in on some browser to a Google account, like log into your Gmail, then in that same browser, a different tab on the same browser, drop this URL, which is right in the chat. Dieter, look at the bottom of Dieter's post in the chat that he just put there. Copy that, paste it into your browser. Then you have a read-only version of what we'll be covering today. You can run it, but it's read-only. But if you make a copy of it, you can save it, rename it, change it, share it, make it your own. You can use it for your own learning or teaching, or if you want to put it on your CV or LinkedIn after you've made some changes and made it your free. Also, last week there was a collab that you can keep as well, but that was more focused on NumPy and data frames, which are the basic building blocks for doing a little bit of data science that we'll get into today. Okay, so I have copied this and I go to a browser where in a different tab, I'm logged into a Google account. Now, let's say I want to make this my own, make this a little different from what you're seeing. Say file, save a copy in Drive. Now we're creating a copy of it. It'll have a new name, copy of blah, blah, blah. Let's say I can rename it, uh, give it some different name. Then I can make changes. Like if I click here on the edit, uh, let's say I want life after code in place, so the lowercase a. Then I close it. Then if I were to save it, now I've got a slightly different version. It's got a lowercase a here. And there's two ways I could save this or share it. I could do file, download as an IPYNB. Then I would It'd be less than a megabyte, I think, but it would download it onto my hard drive and my computer. That's one way. Or another way is just by URL. I can share it. Okay, I can share it with certain email friend, just certain emails, or I can share it with like everyone at San Jose State or everyone who has the link. So if I share it with everyone who has the link, then if I grab this and send it to whoever, anybody, they could see it. Like if I wanted to put this on my LinkedIn or my CV or what have you. So let's talk now a little bit about data science. So again, you can make copies of this. We'll look at some data sets and you can grab your own data sets and do your own experimentation with this without being a data expert or a hardcore Python expert. That's one of the beauties of this, of because Python has a lot of nice open source materials that allow you to do a fair amount of things related to data. You can, and again, so Colabs is free and everything is not running on my computer or your computer. It's in some Google Cloud somewhere. Now, these are the three libraries that we talked about last week. And these are the basic building blocks generally for data science. NumPy numeric stands for numerical Python. Import that, and you can work with arrays, lists, and dictionaries in Python. And Python in general are pretty slow, but NumPy gives you these arrays, and they're actually most of it is implemented in C or C++, and it's pretty fast. So, and it doesn't matter if we're dealing with hundreds of items, but if we're dealing with hundreds of thousands of items or millions of items, like is the case if we're doing hardcore data science or artificial intelligence, then you want things to be fast. And that's why NumPy and Pandas data frames are used heavily in AI and data science when dealing with large amounts of data. And Matplotlib is the plotting charting library that's used a fair amount as well. So let's use a real CSV data set that's out there that has questions about happiness in the world. And we'll use pandas to load the data. We'll use NumPy for the mathematical operations, and we'll do some graphs with Matplotlib. So we don't want to just run the code. We want to use the data to ask some questions. So do some analysis. So we'll explore things about countries, their economies, their the health in those countries, and the happiness in those countries. So when we click on this run button, it runs this Python code in a Google Cloud. It takes the first time you click on it, it takes a while to establish the connection. Then it gets faster. But this being a capital, this is a constant, and this is just a string. The string is the name of this CSV file. It's the URL address of the CSV file. Now, this next line is pretty powerful. What's going on here? PD is pandas. So this reads CSV. So it takes this string, this URL, it goes out to the internet, reads the comma separated values from that file, and puts it into a data frame called happiness. So this is a data frame with 153 rows and 12 columns. So a data frame, it's conceptually a bunch of rows and columns. It's conceptually kind of like an Excel spreadsheet that has rows and columns, or a database table that has rows and columns, but it has this nice ability to do mathematical operations on the rows and the columns. And this data frame is used very heavily in data science. So we've got this, think of it as if you prefer, as an Excel spreadsheet or a database table, but this data frame called happiness, it's got a bunch of rows and columns. In the head command with no parameters will show the first 5 rows. But if you give it a number other than 5, you'll see 7. I chose 7 just because I'm proud of the fact that Canada's in the top 7. Okay. Other than that, it's pretty random. But this now, of the 153 rows, this shows the first 7 rows. It's always good to look at the data to see what's going on here. We see these columns, the name of the country, the happiness rank. That means, according to this happiness scale, Norway is the happiest country on the planet. They've got this happiness score of 7.5. They've got high scores across the board, economy, family, health, etc. And if you go down here to the 7th place country, Canada, the score is a little bit lower. It's still, out of the 153 countries or whatever, this is still has relatively high scores. If you want, we can look at tail. We can look at the bottom 7. And so we see the bottom 7 countries in terms of happiness. Here's their rank, here's their score. Instead of 7 point something, it's 2 or 3 point something. And we've got zeros here for economy and family. Now, one thing about working with data, your conclusions are only as good as your data. No country has an economy of 0, right? So that's bad data right there. So your conclusions are only as good as your data. And we're not going to spend much time on this, but in data analytics and in data science in real life, people spend a lot of time cleaning the data. That means if there's missing data, inaccurate data, data that obviously looks wrong or is irrelevant, there are steps to address that. You can default them, not use that data. There are various methodologies for handling that are beyond the scope of this talk, but just keep in mind, in real life, you often need to work with that. When you've got a data frame, you just say dot columns, that'll give you a property of all the column names. And here it shows us the column names. And you call it info with parentheses. It'll show you, okay, for the 12 columns, give you a little bit of information about those columns. It'll tell you if it's an object, if it's an int or a float, or an object which could include a string. It'll tell you if it's null or not. Now, we see here, of the 153 items, 153 rows, job satisfaction is totally missing for 2 of these. And we also saw up there that sometimes we had an economy, that at least one country had an economy and a family where there was data present, but it was a 0, which is awfully suspicious and probably bad data.
So Doug, this ties in with a question in the chat about how if missing columns will mess things up. It looks like maybe you're getting to that.
So missing columns or
Or
columns that
not missing columns, sorry, missing information.
missing information in the columns or columns that have bad data, like a zero, when zero makes no sense, will absolutely can mess things up. So sometimes you just omit that data, or you could default it to something. Um, and I'm just going to mention that. And there's lots of capabilities in data frames for how to handle that. There's lots of strategies for handling that. Like the two simple ones are just default it to some value or just drop those rows.
So any conclusions you draw from the data are only as good as the data set going in. So garbage in, garbage out.
The big
Neat.
picture. Yes. Yes. Exactly.
Thanks.
Right. So we can look at here at ones that are actually missing and find, okay, only one column. For one column, only two rows are missing. But we also saw there are some zeros that don't make sense as well. There are ways to address that as well. So whenever you work with data in real life, you need to figure out, okay, what does this data represent? Uh, what does each column represent? Are some values missing or invalid? And if so, how do we handle it? But we won't go any further in that. I'm just saying that's what you need to do sometimes. So we can also describe some summary statistics. Like we see this number, happiness, uh, economy. What are these numbers? Well, if we describe this, do a describe on the data frame, it can tell us, well, again, we've got 153 rows. It can tell us what is the mean happiness score, standard deviation, if you're interested in that. What is the minimum happiness score? What is the maximum happiness score? Because when we hear 7.5, it's like, what does that mean? Norway had a 7.5. What does that mean? Well, I still can't tell you exactly what it means, but I know it's the maximum, and the minimum was 2 point something, and the mean is 5.3. Mean being add them up and divide them by the number. The median, which is the middle score, is slightly different. It's 5.2. So there's a lot of statistics here. You can look at the bottom 25% or the top 75%. This describe can get you a lot of useful information. So we can also sort the values as well. We can sort them by the happiness score, ascending or descending. So now we've got here a different data frame with only 10 values because we got dot head with no parameters gets you the top 5. Here it gets you the top 10. It's sorting by the happiness score in descending order because we want the happiest. Norway is a 7.5 of these 10 countries. The lowest is Australia with a 7.2. So we want them in descending order if we're sorting by happiness score. If we're sorting by rank, we want them in ascending order. You have to think about ascending or descending. So here we've got a small data frame. We mouse over it. Colab will nicely show us it's got 10 rows, 12 columns. And when we print it out, if all we care about is the 10 happiest, all we care about is the overall score, what region they're in, and we don't care about health, economy, generosity, those other columns. Here we just have these three columns. So this putting a list here of column names says, get me a new data frame with only the, yeah, this drop NA will will drop missing values. That will not drop to zeros, but there are ways to do that as well. So now let's display them the lowest ones because we've got we're sorting by ascending is true. The happiness score, remember, a low value means below happiness. So the lowest values are the most unhappy countries, which is Central African Republic. But that could be partly because they had a zero for economy, which is probably bad data. So at least this one, uh, I wouldn't trust that conclusion because of those zeros in there, which looked looks wrong. So we here now, if you want to put your own country in here, you can just put your own country name, figure out figure out where or some other country. Like here, I put in Canada. Canada's rank is seventh out of the 153. This is the happiness score, and these other scores. Now, offhand, what does a generosity of 0.43 mean? I don't know, but if we come up here, we can find out that the mean generosity is 2.4, and the maximum generosity is 0.83. So that gives you a feel that this is a pretty good score for Canada. And I won't spend a huge amount of time doing this, but things that you can do if you'd like, you could put in some neighboring countries you visited. You can find out the mean and median, min and max scores for all the countries, and then see how whatever country you look at stacks up compared to that. And what's nice about this is you can do this without being a statistics expert, without having to do the math yourself, and with not much Python code, and just by following these examples, because there's a lot of capabilities in NumPy and Pandas and Matplotlib. So mean is what we think of as the average, all of the values divided by the number. Median is the middle value. And if they're close, it means we have a reasonably balanced distribution. So here, let's plot all of the happiness scores. We had Norway and some other countries that were well above 7. We had a couple countries that were below 2. This shows there's a lot of countries in the 4 and 5 range. It shows the number of countries. So, and this number of bins here says, okay, we've got 12 bins, 12 bars, so to speak. Well, we can get a different view if we make a smaller number of bins. Is that more useful? Well, it depends on what you want. Or a larger number of bins, 35. And sometimes you got to play with it and figure out what gives you the view that's more useful. And if you're presenting this to some customer, your boss, your teacher, your students, there's some trial and error in figuring out exactly how you want to display this. So now histogram groups numbers into ranges. So where are the most countries concentrated? Are very high scores common or very low scores common? Well, we look here, there's not that many high scores. There's not that many low scores. There's a fair amount in the middle. And here we can also do a horizontal bar chart. The nice thing is with Matplotlib, there's a lot of ways to chart things. This just plots the top 10. We get the country name and their happiness score in a horizontal chart. Yeah, so bins again are basically the number of bars, basically. We can also group by region. We saw one of the columns is region. When I first look at this, and it shows that we can also group by region. So happiness, that's a, a column name, and well, that's the data frame, but we group by region and the happiness score and get the mean. We sort ascending and false. We got this one complicated line of code. We print out this new data frame called regional happiness. It only has two columns. It has region and the mean, the average happiness score. And when I looked at this, I was like, okay, North America is high, Western Europe is high, Eastern Europe is above average, Europe is low. I was like, what on earth is Europe? We already have Western Europe and Eastern Europe. I was very confused when I saw that. So I'm like, okay, let's see what countries are in Europe. We can do that in one line of code. Europe happiness is a new data frame, which will look at the happiness data frame, the big data frame of 153 rows, and it'll filter out and it'll only get the countries where the region is Europe. And then in this next line, we will print it. And when we run that, we see that the countries that are in Europe are just one country, Ukraine. And yeah, it's probably not happy when you're at war, right? So that's that satisfied my curiosity. Is like, what on earth was that in the data? To me, it's odd that the data has a bunch of countries in Western Europe, a bunch of countries in Eastern Europe, and one country in Europe. So what if we want the overall European score? Well, we take this happiness data frame that has 153 rows. We grab this means or. We grab the countries, the rows there where the region is Western Europe or the region is Europe or the region is Eastern Europe. And we put that in this data frame with one line of code, and then we can print out the overall mean score for all of these. So when we run this, when we mouse over here, we find out there's 42 rows that are some type of Europe, and the mean score for that is well above average, almost 6.1. We can graph all the regions with a and we show them by region, and we see these various regions with their scores. So obviously these are doesn't describe every person in every country in that region. They're, I don't know, samples of data. I cannot vouch where the for how the data was gathered. I would be guessing, but the averages summarize the data. They also can hide differences. So data science requires both calculation and important interpretation and, yeah, garbage in, garbage out. Sometimes there's a lot of data and you need to figure out what pieces of data you actually care about. Now, what columns do we think are relevant or are really significant factors in influencing the, the overall happiness? Question? So let's look at the economy versus the happiness score. Let's do a scatter plot, which is just plotting a bunch of dots of economy versus the happiness score. Well, the y-axis here is the happiness score. The x-axis is the economy. And there's a lot of variation, but we do see a positive correlation. Positive correlation means as one of the values goes up, the other value goes up. We see in general, as the economic value goes up, the happiness score goes up. Now that does not prove causation. That does not prove that a higher economy causes higher happiness, or it does not prove that higher happiness causes a higher economy. But this does illustrate there is some relationship there. So it shows there is a positive relationship, but you can't claim one can cause the other. Now, there are some statistical approaches that can show causation, but that's beyond the scope of what we're going to be talking about today. This chart by itself does not illustrate causation, but there are times that, let's say we're dealing with medical data or what have you, there are statistical approaches that can demonstrate causation, but they're more complicated. We're not going to get into that today. So now let's look at health versus happiness. Well, we got health here and we got happiness here. There seems to be some correlation as one goes up, the other goes up, but it's perhaps a little bit weaker than the last one we looked at, perhaps. But it's hard to say looking at it. When we look at this, the happiness versus the economy versus this, you might be able to say the happiness one, there's a little more correlation. It's kind of hard to say. Now, freedom is another column. What it exactly means, I don't know. But um, again, I'm not intimately familiar with where the data came from and what freedom means in this context. But if we look at this, can we see a positive correlation? Drop a Y in the chat if you think there is a positive correlation, and an N if you think no, there is not a positive correlation. We got some Ys. Yeah, I think there is. It's not quite as obvious as the other ones, but I think that there is. Now, sometimes it's difficult just by looking at these. Can we do this programmatically? So here, yes, we can. Dataframe.core will give us the correlation. correlation only on the number ones. We're not going to try and correlate by region. I mean, that's a string. What does North America or South America mean? It's hard to associate meaning for that. But for the numerical columns, even if we don't know what freedom is, we know it's a number. Even if we can't exactly say what generosity is, we can say it's a number. So when we run this, this will give us some correlations. Now the happiness rank is a correlation of one. One means it is so obvious that as the X value increases, the Y value increases. Well, the happiness rank and the happiness score are essentially the same thing. Um, Norway, the happiness rank, they had won the highest rank um, as it goes up. The happiness score, well, that's more or less -1. That's an, uh, an inverse relationship. Why is it negative? Well, a high score, a high happiness value, like Norway had the highest happiness value, but it had the lowest happiness rank. It was number one. High happiness meant the lowest rank because we're ranking the number one, meaning the best. Number seven was Canada, above average, but it has a low number, whereas Central African Republic had a low happiness score, but the highest happiness rank of 153. So that's not a direct correlation. That's indirect, which would be -1. But we can see here the a lot of these are positive. Stronger economy means a stronger happiness score. So we looked at the economy. We pretty easily saw there was a strong positive relationship there. We looked at health. It looked like it was almost as strong. For freedom, there was still a positive correlation there, but it wasn't as strong. So the I don't want to get too much into the statistics, but just using this can show you which columns correlate strongly or weakly in a positive or a negative way with whatever value you're looking at. But here it's like looking at the happiness score. So the correlations range from -1 to 1. 1 is a very strong positive relationship. As one increases, the other increases. -1 is the strongest possible negative relationship. As one increases, the other decreases. And if the closer it is to 0, the weaker the linear relationship. Like if you've got a bunch of dots that look totally random and you're trying to see, is there a positive or a negative relationship between the X and the Y axis? And if you can't conclude anything, that would be a 0. And again, we can look at which variables are more strongly related. This is basically sorting those. Job satisfaction is the highest one above the economy. And generosity has a slight correlation, but it doesn't have a strong correlation.
Oh boy.
So again, we can do this. We can pick certain, just do this for a subset of the rows. We'll just take these 5 countries. Let's say we don't care about all of the columns. We just care about these 6 or 7 columns. Then we can sort these and see the values here just to see what you, if you don't want to look at all 12 columns and 150 rows, let's say you figure out after a while, I only care about these 6 or 7 columns in these 5 countries. You can narrow this down so it's much easier to see and to work with. So there's a lot of ways to slice and dice the data very nicely with these data frames with a very small amount of code, and there are many more than this. Question, Steve?
Yes. I think I know the answer, but I'm going to ask it anyway. When you say the strongest correlation, it could as well be a negative one,
Yes.
right? Yeah, okay. Good. That's
Negative one would
sure.
be an extremely strong negative relationship. If you look at the dots, you can see very clearly as one value goes up, the other goes up. And if you want, you can on your own look at different countries, look at different stories. Leave that for you if you to on your own. So here's the same thing, the happiness scores for those countries with a horizontal bar graph. And as we saw last week, we spent a little more time on Matplotlib. You can do pie charts and all kinds of charts with Matplotlib relatively easily without much code. We're just using a subset of those today, a subset of the ones we looked at last week, which is a subset of those that are available. And some questions you can think about on your own is, were some of these surprising? Which variables seemed most important? But let's summarize what we've done here with this happiness data. In one line of code, pandas.readCSV took a URL that pointed to a CSV file, a comma-separated value file, which might have been exported from an Excel spreadsheet or something, read it into memory into this data frame, pandas data frame object. Then we could look at the first values, get some information about it, describe the data in certain ways. We could filter, sort, group by, plot it, do all kinds of things with it without much code. Now, I kind of glossed over, sometimes you want to look at sometimes there's some statistics involved. You want to look a little bit at the standard deviation. There's a lot of mathematical, statistical operations and data and conclusions you can come to as well that we didn't really look at today. So any questions on this before we move to something slightly different? Okay, so we've looked at how to slice and dice the data different ways. Now we're going to look at what's called classification. So if we're looking with numeric data and you want to get averages, values, you can use approaches like what we've been looking at so far. In classification, you typically want to put things in categories. Is this spam or is it not spam? Is this data a predictor of cancer or is it not? Or those are binary classifications. Or in this case, we'll look at some measurements that were taken about flowers. There's classification is not binary. To me, these are all pretty purple flowers, right? But a biologist knows that this is an Iris setosa, this is an Iris versica, and this is an Iris virginica. And there's this famous uh, exercise that occurred 90 years ago in Eastern Canada. A bunch of scientists measured 150 flowers in a field in Eastern Canada years ago and did some uh, statistical, some analysis on this, all pen and paper, obviously, 90 years ago. But we're going to do it in a more using data science. Again, we'll use the NumPy, the pandas, and the matplotlib. So the measurements that were taken 90 years ago are in this iris.csv file, which is it's a very popular data set. I mean, I pulled a copy of it into this location. You can find other locations of the same thing. But when we run this, we find out there's this shape tells us there are 150 rows and 5 columns. When we look at the last 5 rows, it gives us the length in centimeters of the petal width, the petal length, the sepal width, and the sepal length. I was working with this data for about a year, and it finally occurred to me, what's a sepal? And in this case, it's the length and the width of this white thing in the middle of the flower. So you can do a lot of analysis here without even fully understanding the data. Sometimes uh, some medical person might give a bunch of data to a data scientist, and it might be fields that the data scientist does not know or need to know in detail and can still come up with some statistical conclusions on. So of the first 5 rows, okay, it's actually the last 5 rows. Um, they're all the same type of flower, and they have this number of centimeters for the petal width and the petal length. Now let's look at all 150 flowers. Here are the petal length and the petal width. And we'll do a scatter chart on those. And here are 150 dots showing the petal length by the petal width, but it doesn't say which of the 3 flowers it has. We want to group these. This is nice, but it doesn't tell us which of the 3 species of flowers. But now if we group by species and we do this for each of the names, then we put this legend on it. The legend will give us the key when we run this. Now, this legend tells us, oh, this is the iris setosa. This green is the iris virginica, and then this is the other one. And we can see it's pretty easy to tell the iris setosa. They're just smaller than everything else. Question, Vicky?
Um, Sorry, Doug. Okay, I'm a little bit confused here and was wondering if you can explain a couple things. Okay, so okay, I see that Steve has the same question as I do. In that cell you just ran, there's a term alpha. Is alpha your like error rate? Is it similar to P? And then also I was wondering, how does this cell know to separate your flowers into 3 groups? Because I don't see it anywhere that you're telling it to separate it into 3 groups. And then is there any way you can specify like, okay, I want to separate this into just 2 groups or 5 groups? And then how does it know to label it like Setosa versicolor versus whatever
Right.
else?
So, so I'm not going to get into this parameter. If there are many parameters you can look up, that's just an example of this, but I'll answer most of your questions. This line right here, groups by species, when we look if we looked carefully at all, read through all 150 rows, the species columns, the species column has only three distinct values. The iris versica, the iris virginica, and iris setosa. If there are four distinct values, we would have four things here, four
Got it.
groups. This group by says, let's say we had 100 iris setosas and 50 iris virginicas, it would group them into two groups, not three. So that's what this groups does. And then here it loops through those and groups them for those three groups. It prints the dots. What it's not 50 each. Maybe it is 50 each. I don't know. I don't know how many are each, but it prints each of the dots and this ledge with the and it knows to give it different colors. And this legend says, give me the legend means whatever color you picked, you can let it default, which is what happened here, or you can actually say, I want this color or that color. And it says associate that with the name. So this basically says, give me a legend or give me a key. So yeah, I definitely glossed over that. I'm trying to show some of the capabilities that are here and leave this with everyone. And yes, I'm going through it too quick for everyone to fully grasp all of this, but just to show some of the capabilities here. And if you want to drill down and understand the question Vicky asked in detail, you can search more on how this line of code works.
So you don't have to show us how to do it, but I'm just wondering if it has the capabilities. Like if you have, say, five different species, but you want to force categorize it into, say, two, um, like for, I don't know, statistical purposes or comparison purposes, I'm assuming there's a way to do that. You
Yes,
don't have to like
short answer,
force classify.
like let's say we wanted to call these little flowers and big flowers.
Yeah.
We two groups instead of big three groups. We would make um I don't know if you remember last week we talked about adding it's pretty easy to filter and add a new column.
Mm.
We can make a new column that says size and call it little and big and small. And we could loop through and create a new column for all of these, which is big, value of big for these, and a value of small for these.
Got it.
Instead of looking at the petal length and the petal width, we could look at the size.
Yeah.
That would be the way to do it. Make a new column. And there's also ways to do anding and oring in here as well. But the more common way would be to make a new column to show that.
Okay. Thank you. I think somebody else has a question. I think Marcel has his hand up.
Hey, Marcel.
Hi. Yes, about the same line Vicky was referring to. Just to confirm, with the group by function, it's creating basically a data frame for each subset of the species. So when you then later on run for name a group in groups, then each group variable in each iteration is the data set, but just one subset, right? So group holds a data set.
Yes, groups
A
is
data frame, sorry, a data frame, a data frame.
technically it's a data frame group by, but it's more or less a data frame. Okay, a special kind of data frame. Yes, with three items.
Okay, great. Thank
Yes. So this gives one capability. This can be used for classification. Again, classification, instead of looking at numbers, what's the happiness score for the Philippines? 4.7, or trying to classify, is this flower A, B, or C? Is it Iris setosa, versicolor, and virginica. And this one, we could 100% accurately figure out how to do. Here, there's this middle range where it's kind of fuzzy. How would we handle that? Well, let's write this little code. So let's write this code. We write a little bit of Python to classify these flowers. Now, the first one's easy. If the petal length is less than 2.5, it's Iris setosa. So the petal length right here, if it's to the left of this line, we know it's an Iris setosa. That was not hard to come up with. Now, how do we differentiate between these two? Well, we can't do it with 100% accuracy. But by looking at the data, we can say if the petal width, that's the y-axis, if the petal width is greater than 1.75, it's probably the Iris virginica. So if it's above 1.75, it's probably green. And if it's below it, it's probably the orange. That's what this code is doing now. We did not pull this out of the air. We had to look carefully at the data to come up with this. And then we write this, 8-line of code or whatever Python function that will return either Iris setosa, Iris virginica, Iris versicolor based on the petal length and the petal width. So we make a prediction. Iris is the data frame. We make a new column called prediction and apply. So for every one of these 150 rows, we execute this little Python function and come up with a prediction column, which is going to have Iris setosa, Iris versica, Iris versicolor. So now when we run it, instead of 5 columns, we've got 6 columns. We've got this prediction. If we look at the last 20, we'll see usually the species is equal to the prediction, but sometimes not. Okay, because sometimes our prediction is wrong. But this line of code says, does the prediction column equal to the actual species column? We'll do that for all of these 150 rows, and we'll get the mean times 100. And we'll figure out that, and we'll print it out with a percent sign at the end. And it shows that 96% of the time, this classification function returned the correct classification. And in general, I mean, it depends on your data, it depends on your use case, but if you're 90% accurate, if you're doing 90% accuracy, that's pretty awfully good. Yes, this is classification without machine learning. This is more pure data science classification. So any questions on this? And this is used a lot in trying to figure out if something is spam, trying to figure out if advertising, is good. If there's a bunch of medical data, it's got a bunch of columns that people like me who are not biologists don't know what they mean. You can look at the columns and figure out which ones have a correlation to whether a patient actually has cancer. So how do you determine the percentage of accuracy that's acceptable? It depends. There's no one answer for that. It depends on what you're doing. You have to know, it depends on your data. Good question. There is no one set answer. So I'll just talk briefly about another charting library that's used in both data science and machine learning, Seaborn. And you don't use it to train the model, but to see if the model is working. This does not replace Matplotlib, but sometimes it supplements it. It can give you a little bit of information. Here we had those 4 columns, sepal length, sepal width, petal length, and petal width. And if we just do a pair plot, we can look at these and figure out which might be useful things to look at. Like here we can figure out if we look at sepal length compared to sepal width, well, that might not be too useful. But if we compare petal length to petal width, that was useful. But also if you compare petal length to sepal length, that could have gotten us good information as well. And if you're trying to figure out how to predict this looks like it might be useful. Maybe we get better than 96%. I don't know. But if we look at sepal length versus sepal width, that's less confusing. Okay, so let's just spend this much time looking at machine learning. Now in data science, you, the programmer, or your boss or whatever says, I want you to look at this column, this column, this column, and draw some conclusions. Machine learning, to oversimplify, you might give it a bunch of data and say, I don't know what column is useful. I don't know what I'm looking for. Find me some interesting trends here. That's an exaggeration, but it's more in that direction than pure data science that we've looked at. And there is more statistics and probability behind machine learning. There's some in data science that we only glossed over. There's more in machine learning, and we're not going to get into that. But sklearn is the industry standard library with data science, with machine learning that is used on top of, in addition to, the NumPy data frames, Matplotlib. So here we import various subset of sklearn. Why it's got 2 names, I don't know. It's called scikit-learn and it's called sklearn. But here we were just looking at 2 columns, the petal length and the petal width, but there's actually 4 columns. Now, I'm not going to go into detail on this, but in machine learning, you split the data typically into data for training and data for testing. Okay, more, and you do not mix the 2 typically. And on average, you might use half the data for training and half the data for testing. Training means you're looking for trends, and testing means you take the other half of the data and see what trends are there. Do they hold? Now, I'm
Sorry.
not going to go into all the values. I'm just going to talk in generalities. Question.
Yeah, sorry. This library, is it substitution for PyTorch or is it like, what is it?
Th this this is more, so PyTorch, I'm not, let's not get into the difference there. That's, I think this is complicated enough. I appreciate the question, but PyTorch might be more focused on general AI, whereas sklearn is specifically machine learning, which I consider more of a subset of AI. It's an oversimplification, and I'm not really answering your question, but
So in PyTorch, we could do the same thing, right?
Mhm.
Also with using Python language.
Yes, yes, there's multiple ways to do this. In a sense, I kind of view machine learning as data science on steroids. You know, it's taking it further, but focused specifically on more the data aspects of things. So anyhow, we're looking at these 4 columns instead of 2 columns, and we look at features. Feature is a fancy name for column, and target, which is the output. The output is we want to predict the species. Which of these things, these 150 values, which ones are certain flowers? Now we can split the data. Sometimes there's some trial and error. Generally, use half of it for training and half of it for testing. Just with some trial and error, I found we got better results by using 70% for training and 30% for testing. Now, I'm not going to get into this too much, but there are various techniques in machine learning, and random forest is just one of them, and it builds a bunch of decision trees. I'm not going to go into it, but under the covers, there's a lot of if-elses that go on, and it does a lot of if-elses, looks at the data, and kind of comes up, averages them out. And it makes a prediction based on those 4 columns. And so we have this model, which is a random forest classifier, which is a statistical technique, basically. And we do this training on it with a subset of the data. Then we do this prediction on it. And here's the accuracy, which looks at, like before, we got 96%. Now, this is a bit hokey. I had to play with these numbers and change from 50-50 to 70-30. But with a little trial and error, actually was able to get 100% accuracy on this using this random forest classifier and using the 4 columns instead of the 2 columns. We were able to 100% accurately predict the values of what type of flower we're dealing with. And so again, that's just one algorithm. And again, just glossed over this. But another algorithm is the nearest neighbor algorithm, which is used in data science and machine learning. If we get a new flower, 151st flower, how do we predict what it is? Well, we just looked at the nearest neighbor, or the nearest 5 neighbors, the ones that are closest to it on a chart. If we charted it, you know, the various X and Y, even if it's a 3-dimensional or a 4-dimensional, we add up the distances and we look at the closest neighbors, and then usually not the single closest neighbor, but the K nearest neighbors. And you always want an odd number. So when you vote, you don't get a tie. And like if we pick a new flower, 151st flower, we look at the 5 flowers that are closest to it, and if 3 of them are Iris Versica, we guess this is an Iris Versica. So the concept is pretty simple. There's some math behind it. It's kind of like you've got this Pythagorean long line that you're looking at. And in this case, it might be in 4 dimensions, but basically you're looking at the nearest neighbors and just looking at the ones that are the closest. Yeah. And so Primo, they made it calculated mathematically by hand at some initially. I do that in classes I teach too, so that you appreciate how nice it is. You can just do this with a couple lines of code. And, but also the teachers aren't just doing that to be mean to you, Primo. They're doing that so you appreciate the statistics behind it. So a couple of the algorithms that are used are the k nearest neighbors and the random forest. And in the random forest, basically you do some random sampling and you look at some random features. Instead of saying, I care about the petal length and the petal width, um, it does some random, it can choose some of those things randomly. And then it can choose things. But there is something called the curse of dimensionality, meaning, okay, here we're doing four-dimensional analysis of 150 data points. That's still very fast. Even though that's n to the fourth, Google can crunch this really quickly, as we've saw. It appears to go like this. It's in some Google cloud somewhere with a lot of compute power behind it. But if we've got thousands of data points, and if we tell it to do this for 10 columns, that, 1,000 to the 10th, even if it's taking some shortcuts and doing some sampling, it can get really slow. And Google Colab will kind of throttle you and say, yeah, I'll give you the answer, but you might have to wait a lot of seconds or minutes or even hours for this. So when you get up to a lot of columns with large amounts of data, you sometimes need to show some restraint and not look at all of the columns. So again, this is just to give you a, the briefest of introductions of how machine learning takes data science a little bit further. So today we looked at using Google Colab. We reviewed the Python NumPy, Pandas, and Matplotlib to show some nice capabilities for data science. And we took the briefest look at machine learning, at how that goes further than data science. And we didn't really get much into the statistics, but there's a fair amount of statistics and probability in this as you get further, as you get heavily into machine learning and AI. There is a fair amount of underlying math behind it. It's not just computer science, there's a fair amount of math concepts behind it. Now, Python will give you these nice open source packages that have all these statistical capabilities, but you need to know what statistical things you are looking for. And as far as, I'm not going to get into details of overtraining, but to Robert's point, there's no specific rule of thumb, but you need to be careful not to tune the algorithm too much to your specific data, or that could be called overtraining. Sometimes if you get too fancy, like that Python code that we looked at that looked at the petal length and the petal width. If we added a lot more code, we probably could have gotten more than 96%, but it might be overtrained to our little 156 flower data set that might not really apply to other new flowers out in the wild. Yeah. So I want to thank everyone. And again, next week, Vicky will be taking on a new subject. It will be 1 hour earlier, looking at pillow and graphics. So I think that'll be a very good session. And thanks, everyone. and everything will be posted before too long. Thank you.